Okay, we are recording now, and we're still sort of waiting for students to show up. I just had a question before I turned on the recorder about uh, am I getting all of the work? And I was just trying to explain I am getting work from last summer, I'm getting work from the first mini term, I'm getting work from this class, from this term. I'm teaching right now. I'm in 7 classes, so I've had stuff coming in through the years, okay, and I'm just behind in grading and behind in printing, and I've been having some difficulty with the internet. I'll be fine, and then all of a sudden the internet will go out, and if the internet goes out, of course I can't print anything else. And then we're also set up so I'm in one bedroom upstairs and the printer's in another one, because this is an old house and it doesn't have very many three-prong plugs, and the printer has to be in one and I have to be in one, and it's just been kind of crazy. And so it's a what do you call it, wireless printer, and if the internet goes out I can't speak to the printer. So it's been really bizarre, and every now and then my wireless will just take me off the one that goes to the printer and put me on one downstairs that my wife uses. It's a little bit better signal, even though I'm upstairs and it's downstairs, but I'm directly above the room where it is, or the wall where it is. And so sometimes it just cuts me out and I can't print. I don't know why until I check and see that, oh, it just changed me to a different internet. So anyway, it's kind of nuts. I'll try to get caught up. There's not going to be much time today. Tomorrow I may have to go in for blood work, because I said I'm scheduled to have an appointment, an infusion on Friday, and if I can get the blood work done in the morning, that's going to be good. I emailed the doctor over the weekend to see if he would put the order in, but he hasn't emailed back yet, or at least not. And by last night he hadn't emailed back, so I'm going to check on that. I'll have a couple of hours in the morning, except for when I have the blood work done, and a couple hours in the afternoon, and maybe a couple in the evening, that I can try to get some of that printing done and grading. Now, while I'm at my infusion, that's where I take my grading, and I grade while I'm being infused. So at least until the Benadryl knocks me out. So anyway, I'll try to get some of the work graded Friday, and then maybe into the weekend as well. So sorry about that. I am running behind. Any other questions, issues, or problems, concerns? Good. I'm glad you asked that. And we only have 5 people here, so I'm probably going to have to repeat this several times. I think I told you all last week, maybe twice last week, but let me do it again now. I don't know if you're aware of it, but it looks like to me that spring enrollment must be pretty down, okay? And I think the administration was getting kind of antsy about that, so they decided to have a week, almost a week, of intensive advising and registration effort. That's this week. It started yesterday morning at 9 o'clock, and it goes until Thursday evening at 7 o'clock, okay? Monday through Thursday, 9 in the morning till 7 in the evening. They've got tables set up in 2 locations. On the Birmingham campus, it's in the new Academic Success Building. That's the one that faces Wilson Road, but you can't enter it from Wilson Road. You have to turn in the street at the light, come around sort of the back side of the Academic Success Center, and then park back there behind the building and walk into the building from the back side. The front side, the showing side, is toward the Wilson Road, but I don't know if any of those entrances even work. I assume they do, but okay, I hear noises. I don't know what's causing the noise. So anyway, somewhere in that big old building, either upstairs or downstairs, there's some big room that they've set aside, set up tables, and plenty of distance between tables, plenty of distance between everything, and there you can get academic advising and help with registration. Remember, nobody can register for you. This new system we have called Banner, you have to register yourself. So, but they can help you with the registration. They're just separated by a piece of plexiglass, I think. So it's not going to be directly one-on-one, but they can help in any way they can. And they will. And it's mostly going to be faculty manning those tables, but it will be some administrators and possibly some support staff as well. So you should be able to get help. There will be, on the Birmingham campus, 2 tables for general studies, 1 for pre-nursing, 1 for health professions, and 1 for career tech, and I believe 1 for business. There may be others, but I know there's that. There will also be tables in there for financial aid and probably a lot of different things, anything you would need, perhaps even the registrar's office or something like that, so that you can get any questions answered in one room, a big room, but one room, and you'll have to stand in line probably a little bit, not too bad, and you will need to social distance. Everybody has to have a mask on. Everybody. You cannot, I'm not even sure you can get on campus without a mask. I know you can't get into a building without a mask. So be sure you come with your mask. They may have some available for people who forget theirs. I wouldn't bank on it. I would carry my own mask. Okay? So please, if you are going to take advantage of that, go prepared. What I would recommend is that you go to the Virtual Advising Center, get your advising done there. You can be talking with someone one-on-one without any distance in between you because you're talking on the telephone, and you can get all the advising you need, and that person may actually be able to help walk you through registration. Of course, they can't see your iPad, your computer, your phone, or anything else, but you can ask all the questions you want to. But if you really feel like you need more of the one-on-one stuff, that's going to be this week, Monday through Thursday, 9 to 7 in the evening. Now, on the Bessemer campus, that's in the Ethel Hall building. Now, that's not to be confused with the Ethel Hall building on the East campus in Birmingham. This is the one on the Bessemer campus. There's 2 main entrances to the Bessemer campus. One is at the light where the hospital is, okay, or across the street from the hospital, and one is a little bit further down the hill from that, in between the Civic Center, Bessemer Civic Center, and the hospital, okay? Hospital is on one side, the college and the Civic Center on the other side. So if you go there, if you go in the entrance that's in between the hospital and the Civic Center, then you're right in the parking lot you need to be. The building to your left is the Ethel Hall building. You'll see the name on it. And what you'll do from there is walk up the side of the building, park in the parking lot where students can park, walk up the side of the building and come in the side that's opposite the parking lot. That's the main entrance to the building. When you go inside there, the auditorium is immediately on your left. Now, it's not an auditorium like A.G. Gaston or one of those nice auditoriums. It's just a big, big empty room. But they'll have tables set up, 1 for general education, 2 for career tech, 1 for pre-nursing, 1 for health professions, 1 for business, and maybe some others, and probably financial aid and that kind of stuff. So they'll have everything in that big room that you need. So if you really want the one-on-one, go there. But again, take your mask, be prepared to social distance, and get it done. My advice, please try to get your virtual advising center and do it on your own, so you don't have to be around that many people. But if you really want to and need the assistance, take advantage of it. It's all week this week, Monday through Thursday, 9 in the morning until 7 in the evening. Okay, that's my paid political announcement. Are there any questions on that or on anything else? Okay, hearing none, where we are now, we're in Chapter 6, Electricity, and we're on page 152 if you've got the big book, 6-13 if you've got the smaller book, and I thought I had this all set up. and now it's not. So let me get this reset up again. This is the biggest pain in the neck or some other body part I've ever seen. Okay, and we'll go from current slide, and whoa, it jumped the gun on me. Okay, last time we finished talking about characteristics, features, factors that enter into resistance, and now we're on page 152, electrical power and work. So okay, here's what we're going to do today. Hopefully we'll finish chapter 6. Now if we don't, we have time next week to continue in chapter 6. Okay? Today at 5:45 we'll stop and have the lab on Ohm's law that we talked about last time. No, wait, we did Ohm's law, didn't we? The one on that we just did, the resistance lab. So we'll do that resistance lab. And it probably won't take us the full 2 hours, but there is a bit of calculation in it, so stand by for that. Okay, I keep hearing noises, but I can't tell where the noises are coming from. If anyone needs to chat with me, go on and say it, because if I pull it up, everyone can see it anyway. But if you're chatting among yourselves, that's perfectly fine. But I just keep hearing noises that I get no indication what the noise is there for. Okay, so we'll do this today. I'm sorry, this is only Tuesday. Yeah, that's right, I'm sorry. Wait. Yeah, I think I'm a bit ahead of myself, because we have 2 days to finish chapter 6, so there's no huge rush at all. So even if we don't finish today, we can finish on Thursday. And I'll also give the next lab, which it will be on Thursday, and then Thanksgiving week is next week. There's no classes at all during Thanksgiving week. We have professional meetings on Monday, Tuesday, and Wednesday, but then the Thursday and Friday the school will be closed because of Thanksgiving holiday. So if you have business to attend to at the college, either virtually or in person, preferably virtually, then please get it done Monday, Tuesday, and early on Wednesday, because they start letting people go sometime Wednesday afternoon. So don't bank on an office being open with the person you need to talk with late on Wednesday afternoon. The odds are they'll let people go a little bit early to get home and get those turkeys going. So try to get your business taken care of Monday, Tuesday, or Wednesday morning. Okay. You may even find people will be taking off on Wednesday, personal leave or vacation or something like that. So the earlier you can get things done next week, the better. Okay. Now, so then when we come back from Thanksgiving, we'll have basically 3 days to do chapter 8. And chapter 8 is sort of a long chapter, a lot to do, but right now I only have 1 lab prepared for it. If I can come up with a second lab or even a third lab, I think 2 is all we'll do at best. And I do have a second lab done. It's just whether, let me ask this question. Do most of you have access to a book somehow? Yes or no? Especially the no's. Does any of you not have access to a textbook? Either e-book, physical book, big book, little book, some type of book. Does any of you not have access to a book? Anybody? Okay, I'm going to assume that means you all have access to a book. With that assumption, then we will have 2 labs for chapter 18. Okay, and we'll have class. Okay, here comes somebody. I think it's Tobias. Okay, let me get Tobias marked here. Well, oh, I had the wrong grade. I was looking at that other thing about that other student, and I had the wrong grade book open. Well, I'm now dropping everything out of the grade book. So I'll be with you in a minute. Some of these have been graded, but some of them haven't. Okay. Now, okay, finally I'm back running along. Okay, Tobias is here. Okay, has anyone else come in? Yep, here's someone waiting now. I can't see who it was, though. They blacked me out, so I can't see that. Rodrigo is joining, so he's coming in. All right, so that should give me 4, 5, 6 students here, 7 total. Whoa, I am missing somebody. I've got Amia, Angelita, Daniel, Gerald, Tobias, Thomas, and Rodrigo. Hi, I forgot to mark Angelita when she came in. I remember when she did, but I forgot to mark it. That gives us 7 students, and that's what's being indicated. So good deal. All right. Any questions then about how things are going, which direction, that type of thing? Okay. So we've got this week to finish chapter 6, next week and the first Tuesday of the next week to finish chapter 8, and then you'll be turning in your final exams by that Thursday of finals week. Any questions on that? Like I said, we got at least 1 lab. I think I've got 2 labs lined up for this week, and yeah. And then we've got at least 1 and possibly 2 labs lined up for next week. The finals week, I'm not planning to give you a lab for the last day of finals because you already have your test for chapter 8 and your final exam, so I see no reason to add another lab on top of that. So how does that sound for winding things up? Any questions? All right, let's pick up where we left off last time, and that's in electrical power and electrical work. This is on page 152 in chapter 6, electricity. The section this is in electricity is 6.2 electric current. Okay. Now, there are 3 basic circuit elements that are necessary, absolutely required for electrical circuits to work. One of these, you have to have a voltage source. You have to have something that's giving the energy to the charge so it can do work. Okay? So that's your voltage source. That could be a battery if you're dealing with DC current. It could be a solar cell or something like that. That could be contributing to DC current. Anything such as that, or you could be plugged into a wall. If you're plugged into a wall, that's usually AC. Okay? So you need your voltage source. Secondly, you need some sort of device in the circuit to use that energy that your power supply or your voltage source provided. Okay? That would be a heater, a computer, a television, a hot water heater, a refrigerator, whatever it is that you're using, your electrical device that's using the energy that your voltage source is supplying. And then number 3, you have to have conducting wires to connect everything together. Okay? Now, the voltage source provides the potential difference in the circuit, and the conducting wires provides that potential difference across your device. You have an input wire and an output wire. Now you may say, hey, I only see 1 wire here. Okay, that's all I see is 1 wire. How can there be input output? Guess what? There's at least 2 strands of wire inside that casing. guaranteed. You have to have a potential difference across the device. Even across this little microphone, there has to be a potential difference. The input wire is at the higher potential than the output wire. And we'll see some pictures of this that'll show it a little bit better than just words. The output wire is often called the ground in AC circuits. Okay? Now, for those of you who are familiar with AC circuits, you may say, wait a minute, there's two grounds, aren't there? And you would sort of be absolutely correct. Okay, and here comes somebody else. Jacob is coming in. So let me get Jacob here and marked in the book, and then we'll go on from there. Okay, Jacob is here. So the middle part of the alphabet is kind of steaming ahead of the beginning and end. The beginning is doing quite well. Middle, pretty strong. It's the bottom part of the alphabet that's poor old Tobias is having to hold down all by himself. So hopefully some more will be coming in there. And there's a big gap in the... Say again? All right, that's fine. And that was who, Jacob? Okay, yeah, well, we're just glad to have you here. And since you did get here and several others have come in recently, just want to say this, I'm trying not to say it as long as I did the first time, but they're having a big push for advising and registration for spring term this week. It started yesterday morning at 9 o'clock, and it will go till Thursday evening at 7. 9 to 7 every day this week, Monday through Thursday, and they got tables set up, one set in the Academic Success Center. That's that new building on the Birmingham campus. That's where the Winona Elementary School used to be. That's now our Academic Success Center. Okay, I don't know where the room is in there. It's a big building with lots of big rooms. It's either upstairs or downstairs, but someone will be there to direct you how to get there. Okay, now my advice to you would be go to the Virtual Advising Center, get your advising there, and you do your own schedule. Okay, but if you really need some assistance, you have some major questions you don't think you can get answered at the Virtual Advising Center, you just want that one-on-one type, almost one-on-one situation, then be sure you go to either the Birmingham campus Academic Success Center, excuse me, I've got hiccups, or on the Bessemer campus, the Ethel Hall Auditorium. Now, that's not to be confused with Ethel Hall building on the Birmingham East campus. That's the nursing building. It's the Ethel Hall Auditorium on the Bessemer campus, and it's sort of on the south end of the campus, right next to a big parking lot, the biggest parking lot out there for students. So there's plenty of parking, especially on the Bessemer campus. I know there is. The Birmingham campus, I'm sure you might have to walk a little further, but there's plenty of adequate parking there too, especially since students aren't on campus that much right now. So please go. If you can't do the Virtual Advising Center and register yourself, please go to one of those two campuses today. Well, today you're not going to have much time. Tomorrow or Thursday, 9 in the morning until 7 in the evening. But realize you may be in physical science lab at 7 in the evening or getting awfully close to it. So don't put it off till then. Try to get it done beforehand. Any questions? Okay. We were just talking about electrical power and work, the three elements that you have to have for a circuit to work, and that's a voltage source which gives energy to the charges, electrical device to use the energy from the charges, and the conducting wires to maintain that potential difference, not just across the voltage source, that's always there, but across the device, the electrical device that you're using. You have to have an input wire and an output wire. The input wire is at the higher potential than the output wire. The output wire is often called the ground in the AC circuits. And a lot of people will also refer to the negative side of a DC circuit as the ground as well. Now, without that potential difference that's maintained by the conducting wires, you would have no current. And a good example of that is a bird up on a wire. Okay, a lot of the wires that you see running between power poles really have very little insulation on them because no one's supposed to be touching. That's why they're way up there on the poles. Okay, and a bird can be sitting on that and not be fried. Well, the reason is there is no ground for the bird. I mean, it's on the high wire maybe, but it's not got a low wire to take the provide a pathway for the current. I'll give you a rather bizarre example of that. When we first moved to Birmingham, well, the first year we rented a place and lived there, but when we bought our house, it was a small 2-bedroom bungalow, and at first we didn't have a pet. It wasn't a very big yard, but we did get a dog after a while, and the backyard was pretty much fenced in. We just had to do a couple of things to complete that fencing, and we had a place for the dog. Well, this dog was so clever that she could find a way to get out no matter what I did. Okay, she had a dog friend next door, and she would go under the fence to go visit her dog friend. But then when her dog friend wasn't particularly willing to play or something like that, she found out she could go over under any fence and get out. And she loved to go and retrieve garbage, retrieve toys, retrieve clothing, retrieve anything from anywhere in the neighborhood and bring it and deposit it in our front yard or on our front porch. So we come home from work and just have everything scattered throughout our yard. Anything of value, we have to try to walk through the neighborhood and find out if anyone knew to whom it belonged. It was a real pain. So I first would put stakes in the ground to try to hold the fence down. She managed to find ways around or through or tear those up or whatever. I later put barbed wire at the bottom to try to discourage her. She had a thick coat of fur. She just went right under the barbed wire. I could see fur being caught there, but never any blood. She managed to get under. Big dog, and she could get under the thinnest layer of wire. So finally our neighbor in the back said the only way you're going to keep her in, because everybody knew what the jokes it was in the neighborhood, that our yard was just filled with stuff, mostly trash. And so he said the only way you're going to keep her in is put electric fence down. He said one time she'll get shocked, maybe try it a second time after that. You can even turn it off. She'll not try it again. Okay, we'll try it. So I ran just a few inches above the ground, okay, an electric wire, okay, turned it on, and it seemed to do pretty well. Every now and then we'd hear her yip, but that thing about turn it off after a while would never work with Casey. She would go up to it, we think, with her whisker and get as close as she could, and if she felt a tingle, she'd back off. If she didn't feel a tingle, meaning we had turned it off, she was out of there. So she was way too clever by half. I mean, way too clever. Well, she also got this clever. If I was in the backyard, she always so happy for me to be back there, and I'd be working in the little garden we had and stuff or whatever. And she'd get right up against me and push me into the wire. And if I jumped, she knew it was on. So that way she saved on her whisker. She was the most aggravating dog imaginable. Very, very bright. But getting back to this potential difference, one time I came home and went back to let her out, and there was a squirrel like this on the wire, he was grounded because he was touching the ground, and he had touched the wire like this. He was frozen in place. Not frozen literally, but his muscles had tensed up. There was a dead squirrel. Okay, so he had potential. The bird on the wire has no way to ground. The squirrel had a very good way to ground, and it got him. Okay, so let's move on from that to power in circuits. And for some reason, I can't get it to advance. Let's see if it will not. There, here it comes. Here is your power formula. Okay, P is equal to IV. Now, if you remember power from the chapter 3 energy chapter, power is the time rate of change of energy. Okay, well, how do you get time and energy out of I times V? Well, that's a pretty good question. I'm glad you asked. Okay, if you recall, what I stands for is current. Okay, and if I can get my pen to show up, of course, if I use the right end of the pen, that would do better. Okay, but I still can't get the pen to show up. Where are you, pen? There you are. Okay, current is charge per unit time. That's what current is. I is equal to Q over T. You might write that as a small q. I think the book does. Q over T. Charge per unit time. Okay? Multiply that by voltage. What is voltage? That's energy per unit charge. Well, guess what? The charges cancel out. And guess what you have? Energy per unit time, which is power. Now, the unit for power, just like it was in chapter 3, is watt. Okay, watt? Watt. That's what it is. Okay? And that's energy per unit time. And over here, this is amps times volts. Okay? And that gives you wattage. Okay? It's one of those formulas, a lot like Ohm's law. Ohm's law is V is equal to RT. IT. V is equal to IR, okay, if I could say it right. This is the same way. You can get two other formulas out of here. First, dividing both sides by V, and that would give you P over V, and here comes Rucker. Good deal. Let me get Rucker present, so hang on for a moment. I'll be right back with you. And Rucker is here. Okay, top part of the alphabet keeps roaring along here. The middle part, kind of vacant. The upper middle part, the lower middle part, doing quite well. And then the bottom part is just poor old Tobias is holding down the whole bottom part of the alphabet as is. Okay, so here's another rendition of it. P over V is equal to I, or you could divide both sides of this by I, and you get P over I is equal to V. So there's three different renditions of your power formula. If you're looking for voltage, it's P over I. If you're looking for current, it's P over V. If you're looking for power, it's I times V. Very similar to Ohm's law. And when you combine it with Ohm's law, you get other formulas. For instance, on this one, well, let's do this one first. Power is equal to I times V, but V is equal to IR. So this would be the same as I squared R. Okay? That is also a power formula. Instead of V, you put IR in there. Okay? And also, instead of I, you could have put V over R. So another form of the power formula would P is equal to V squared over R. Okay? So this shows that if you increase current, you're going to be increasing your power That's energy per unit time, really big time. So guess what, folks? You turn on that clothes dryer, you turn on your oven, you turn on anything that it produces a lot of current or drags on a lot of current, you're going to watch that meter outside spin like crazy, or those digits start moving really fast. Okay. Otherwise, when you have high voltage things like your clothes dryer, your oven, your range, those kind of things, you'll also, when you turn that on, it uses a lot of voltage, and that's going to make that spin pretty quickly too. All right, so we've sort of marked all over power and circuits. Let's see what's next. In your electric bills, believe it or not, even though it's coming from the power company, it's not a power bill. That's what we'll call it. We'll say the power bill's here. No, it isn't. It's an electric bill or an energy bill. Energy is power time, just like we have here, that power is energy divided by time. If you multiply both sides of that by time, you get energy is equal to power times time. Well, guess what you're paying for on your energy bill? It's not watts or kilowatts. You're paying for kilowatt hours, not kilowatts, kilowatt hours. And a kilowatt hour is in power times time. That's what they're talking about here. You're paying for energy, not for power. Okay? Now, this right here is a little bit wrong. This should be dollars per kilowatt hours, because that's what you're paying for. But the way they have it set up here, they make it seem like, well, I think they just got it wrong, because the time would cancel into hours. This would be dollars per kilowatts. You got a kilowatt down here, per kilowatt down here, cancels that one out, and the watts down here cancels that one out. So that leaves you with dollars. Okay, that's what you're left with. That's the rate, dollars per kilowatt hour. So that should be per kilowatt hour. And if you look at your power bill, if your mom, dad, grandma, whoever pays the power bill, the energy bill, take a look at it sometime and you'll see you're not paying for power, you're paying for energy, kilowatt hours. Okay? Any questions on that? Okay. Now, I think that takes us down to example 5 on page 154. So let's see, before we get to magnetism, I think what I'll do is use the white space or sort of light blue space or whatever here. So I'm going to clear my ink here, and let's do example 6.5. A 1,100 watt hair dryer. So what's that a measure of? Measured in watts. Where is the pen going to? There it is. Okay. So this is your power is equal to 1,100 watts. Now that's a lot of wattage, because if you think about it, most of your light bulbs in some places will only be 40 watt bulbs. A lot of places 60 watts. The really high power ones are 100 watts. This is a hair dryer. It's using the heat. Anytime you're producing heat, you're using a lot of power. So 1,100 watts is designed to operate on a 120 volt circuit. Well, that's obviously your voltage, okay? And that's 120 volt circuit. I can almost guarantee you that's going to be AC, okay? How much current does the dryer require? Okay, So we're looking for current. And remember, I had 3 formulas there that had to do with power. One of them solved for current. Which one was that? Does anyone remember? Where is the pen gone? Oh, there it is. Okay. What was current? Current was power over voltage. Okay? And that would be 1,100. The pen writes sometimes and doesn't write other times. And writes wrong when I don't pay attention. Okay? Okay? 1,100 watts. Or you could say joules per second. That's what a watt is. Okay? Divided by voltage, which is 120 volts, and this would be joules per coulomb. Whoops, that's supposed to be a C. Didn't write that one too well, did I? Well, get out of there. Okay, let me see if I can get this to cooperate. Okay, that's supposed to be a C down there. It sort of closed up on me. Okay, well here obviously the joules will cancel out, and this leaves you, I don't have my phone out here yet, let me get that. Get my calculator set up. And that's 1,100 divided by 120, and that would be 9.17 approximately amps. Now folks, that's a lot of current. If I could just find my pen again. Okay, come on pen, where are you? Does anyone see where the pen is? There it is, down there. Okay, so this would be 9.17, and that's joules per second, coulombs per second. Coulombs per second is an amp. Okay, 9.17 amps. Now, I don't know if you remember when I told you before, anything an amp or more is a lot of current. A lot of times we measure current in milliamps, thousandths of an amp. This is 9.17 amps. And what did they say? They rounded that to 9.2. Okay. Okay. And the reason for that, you can't tell. That looks like 2 significant digits. That looks like 2. So we'll round that to 2 significant digits. The 6 over here would have rounded that up to a 2. I wrote a 7 because it was a 6, and I already rounded once. Okay. Now, example 6.6, right underneath there, it says an electric fan is designed to draw 0.5 amps. Well, that's obviously a current. That's a lot less current than this one was, okay? And electric fans do not produce a lot of heat. In a 120 volt circuit, 120 volts, that's obviously your voltage, okay? What is the power rating of the fan? So we're looking for power, that's the unknown here, is equal to P, okay? Well, we know the formula for power. Power is current times voltage, or voltage times current. Doesn't matter which order you do. So this would be 0.5 amps multiplied by 120 volts. And 0.5 is exactly half. Half of 120 would be 60 watts, which would be about like a medium-sized light bulb. Okay, so electric fan probably is not going to draw that much power. Okay, that's energy per unit time, because it's not. The electric motors are pretty efficient things, and it's just turning the blades, blowing the air, and that's probably going to do you pretty good. 60 watts, good deal. Now, let's move on from there. Oh, here's 6.7 coming up too. Now, before we get to 6.7, let's take a look at some things here. Table 6.2, if you got your books, and earlier I was asking how many did not have access to a book, and absolutely nobody responded. Now, I hope you were listening and paying attention and answering correctly, that all of you have some type of book you can use. If you do, we're going to be able to do the last lab in the in chapter 8, because you will need your books for that one. Okay, but if you got your book, table 6.2 is a really good table. It shows you the summary of your electrical quantities and units. Charge is measured as in a unit called coulomb, and a coulomb is the equivalent of 6.24 times 10 to the 18. That's an incredibly large number of electrons times the single electron charge. Okay, so a coulomb, Q is equal to NE. Electrical potential difference, V is equal to W over Q, work per unit charge, joules per coulomb. And the unit, the symbol for electrical potential difference is V. The unit is also V, voltage and volt. Okay, they both use capital V, both named after Alessandro Volta. Electric current is I is equal to Q over T, which is charge per unit time, and that's an amp, named after Louis Ampere, French physicist. Electrical resistance, R, is equal to V over I. That's measured in ohms, named after Georg Ohm, a German physicist. Okay, and that's also a volt per unit amp, if you wanted to write it that way. Electrical power, P is equal to IV. That's measured in watts, and a watt is a joule per second. So a current, which is coulomb per second, multiplied voltage by voltage, which is joules per coulomb, gives you joules per second. Now there's another little blurb called Concepts Applied underneath that, shocking costs, and they're not really all that shocking, but it's just talking about some of the ways that you can measure cost. They love to use this formula that I find is fairly awkward, but it's certainly something you can use. Okay, several questions there, you can look at that. The people behind the science, surprisingly, I don't know if you're surprised at this, Benjamin Franklin in a science book? You better believe it. He wasn't just a statesman, just a writer, just a postmaster general, just a anything. He was a man of many, many, many talents, and not the least of which was his scientific contributions. And everybody pretty much knows the story of him going out in the lightning storm to show that lightning was a form of electricity. Fortunately, he had a key or something hanging down that took the lightning to ground without going through him and using him as a pathway to ground. Otherwise, he would have been dead. Okay, but quite a brilliant guy. Quite an inventor. He invented the Franklin stove, which was much more efficient at distributing heat than the old fireplaces were. There were many things he did, and he happened to also be, if I'm not mistaken, the emissary, perhaps the ambassador to France, about the same time, I think, Louis Ampere and Charles Coulomb, I think when they were still alive and active, I bet you, got together with those dudes and they talk science there too. Now, this blurb in the book is a great source of information, a great source of ideas, and here is Daniel. He must have got booted out or had to leave and then come back. So I'm glad Daniel's back here. I'm sure I've already got him present. Yes, I do. Okay. But this can't be the source for your paper. It can be a source of ideas, but not a source for your paper. You have to find that outside the book. Okay, I'm trying to see if I see any other things in here that may be worthy of a paper topic. I'm sure if you read it carefully, you'll find several things that you might strike your fancy. So let's do example 6.7. Okay, so I'm going to clear my writing here so I can get back in again, and for some reason I can't clear my writing, and I don't see why. This is so aggravating. Here we go. Finally I can clear it. Okay. Now, what is the cost? So now we're looking at for cost. If I could get my pen to operate here. Where are you? There you are. So this is the cost that we're looking for. Okay, this is dollars. Okay, so you won't confuse it with coulombs. What is the cost of operating a 100-watt light bulb? Well, 100 watt is a measure of power. That's your 100-watt light bulb. Okay, for 1 hour. So there's your time. Time is equal to 1.00 hours. Okay. If the utility rate is, and they call this in their rendition, the rate, which is as good a name as any, is 10 cents per kilowatt hour. Okay. Now, I think already you may see that there's some problems here because the rate is measured in kilowatt hours. This is only measured in watts. Okay, so at some point you either need to get the watts to the kilowatts or the kilowatts to a watt. Okay, since this is in the denominator, it's probably going to be easier to do here. So what we'll do is first talk about what the energy is. Energy is equal to power times time. Okay, the power here is 100 watts times the time. Here is probably the best place to change that to kilowatts. To change 100 watts to kilowatt, move your decimal 3 places. So I'm going to change that, if I can get my pen to come up, my eraser to come up. Okay, let's just go on right here and change that to 0.1 kilowatts, because 100 watts, move the decimal 3 places to the left, and that gives you 0.100 kilowatts times 1 hour. Okay, that's a decimal in there, so that would give you 0.100 kilowatt hour. That's the energy you use. Multiply that by the rate at 10 cents per kilowatt hour. So multiply that by 0.10 cents per kilowatt hour. And the per kilowatt hour wipes out the kilowatt hour, and that gives you 0.01, sorry, 1 cent. Okay, 1 cent is the cost of operating a 100-watt light bulb 1 hour. Okay, now that doesn't seem like much, and it isn't really. Okay, My younger brother used to work for an electric power company, and he said, lights don't cost you much, run as many lights as you want to. And he did. He liked to have his house all lit up. The thing is, it still adds up. My father would have said, but my father was already dead by then, so he didn't, well, let him live his life however he wanted to, basically. I still am very cheap like my dad, and I like to turn them off if I'm not using them. But if you think about it, number one, I don't think anybody's electrical rate is still at a dime per kilowatt hour. Okay, I think it's more like 17 cents or 20 cents or 25 cents. It's gone up. So that would make this slightly skewed low. And that's just 1 hour. You pay your power bill once a month. So if you had that 100-watt bulb on for, let's just say, 3 hours an evening, then it would be 3 cents a day at this rate. Double the rate, and that would be 6 cents a day. Do that for 30 days, and you're now up to, significantly more power. I mean, significantly more cost. So it does add up. Don't let them fool you. So you came up with 1 penny per. That's the cost of operating a 100-watt bulb 1 hour at 10 cents a kilowatt hour. Example 6.8, and I think I'll clear this out too, because we don't have a lot of room to write. Example 6.8, an electric fan draws 0.5 amps. We had that before. It's probably the same fan. If I could find my pen. Goodness gracious, where has it gone? There it is. Okay. So the current is equal to 0.5 amps. Okay. In a 120 volt circuit, that's obviously the voltage. If I could get the pen to come back, voltage is equal to 120 volts. What is the cost for operating the fan if the rate is 10 cents per kilowatt hour, just like we had before? I could have left that. 0.10 cents per kilowatt hour. Okay. All right, and that's all they give you. Now, they don't say how long you run it. They say what is the cost. And if you look at things now, let's go back to what we were doing before. You're given current and voltage. That gives you power. Your power is 0.5 amps times 120 volts. This is what we did in an earlier problem. And that gave us 60 watts. That's your energy. I'm sorry, that's your power. Let's get this to kilowatts simply by moving the decimal 3 places to the left, and that would be 0.06 kilowatts. So, I'm sorry, yeah, kilowatts. Excuse me. So if we multiply the rate of 0.1, which is a dime per kilowatt hour, multiply that by 0.060 watt, no, this is kilowatts now because we moved the decimal place, then what you find out, the cost is 0.006. The kilowatts go out, and this is per hour. So the cost of operating that electric fan would be 6/10 of a penny, 6/10 of a cent per hour. Okay, so if you ran that for let's say 5 hours in the summertime, that electric fan, 5 hours in the summertime, that would cost you 3 cents. Okay, 6/10 of a cent per hour times 3 hours would be, 5 hours would be 3 cents. Okay, not a bad deal. And that's all they give here, 6/10 of a penny per hour for each hour. All right. So that wraps up electrical power and work. I probably took way too long on that, but let's move along to the second half of the chapter, which is magnetism. Now, the earliest ideas associated with magnetism, people discovered there were certain rocks, okay, literally rocks. The name for it, the common name, was lodestone, that they would find periodically that were naturally occurring magnetic material. Okay, that lodestone was largely iron. They may not have known that at the time, but it was. And they gave the name of that mineral magnetite, meaning it was magnetic material. There's the word magnet, the first 6 letters is magnet, magnetite. And a lot of your minerals have ITE at the end, so that sort of made sense. Okay, now later it was discovered that hematite, which is basically iron ore, the purest form of iron ore, was basically exactly the same chemical as magnetite. It just happened to be that magnetite was magnetic, hematite was not necessarily magnetic. Now, magnets would stick to hematite, but hematite wouldn't stick to other iron. So magnets will stick to iron, but iron won't necessarily stick to iron. Okay, just plain old iron. Okay, we'll talk about that a little bit later. Now, how are magnets characterized? Well, people found out a very, very, very practical use for magnets pretty soon. They're characterized by poles. One of these poles always points toward the north, and one of them always points toward the south. Okay, so that was very, very handy, especially when you came to navigation, especially on the sea when you don't have anything around you but water. How do you know which direction you're going? You can't look at much. Now, sure, if the stars came out and you knew where the North Star was, you could look at that. Okay, but if it was a cloudy night, you're in trouble. If it's the daytime, you're in trouble. Except for knowing what time of day it was, you can sort of go by the sun, kind of what direction you're going, but it was sort of tough. The magnets gave them far more precision in navigation. That also is true over land too. It doesn't have to be just at sea. I mean, you can be out in the middle of nowhere and have no idea which way north is. Okay, so you can pick up some clues, but you know for sure if you got a compass. Now, there are only three naturally occurring magnetic materials. I've mentioned one was iron. Magnetite is the iron ore that is magnetic, naturally magnetic. Another is cobalt, which is not all that common. And the third one is nickel, which is a lot more common than cobalt, but not nearly as common as iron. Now, these 3 elements are called your ferromagnetic elements. Ferro basically comes from the name for iron. Ferrous is iron. So ferromagnetic. These are iron and its other related magnetic materials. Now, I'll give you a little more detail here. You probably don't care about it. Iron is on the softer magnetic side of this. It's not that iron is soft, but it's easier to magnetize iron than it is cobalt or nickel. But it's easier to lose magnetism in iron than cobalt and nickel. So your soft magnets, they call them, meaning easy to magnetize but also easy to lose the magnetism, are mostly iron or totally iron. Those that have more nickel and cobalt in them are your hard magnets that even though no matter what you do to them, they remain strongly magnetic. But those are your three ferromagnetic materials. Now, for those of you who do have a book, especially the big book, or you can go to chapter 8 and see there's your periodic table, and if you happen to look, right there is iron, Fe, remember, ferrous, there's cobalt, Co, and there's nickel, Ni. I'm sorry, my book's falling down. I'm trying to get it so you can read it. Iron, nickel, and cobalt right there next to each other in the periodic table. In the metals, the transition metals. Now, the modern view, magnetism is associated with magnetic fields, just like electricity is associated with electric fields, like gravity is associated with gravitational fields. Everything depends on those fields. Now, if you remember our convention for electrical fields always point away from a positive charge toward a negative charge because they're the direction a small test, positive test charge would go, away from the north toward the south. Well, your field lines in magnets go away from your north poles and toward your south poles. That's how they go. That's just the convention they came up with. Let's just have them point in that direction. Okay? Go away from north toward the south. Okay? Now, magnetic fields and magnetic poles are totally inseparable. You cannot have one without the other. Same thing with electrical charges. If you have an electrical charge, it's got a field around it. If it's a positive charge, the field lines are pointing away from it. A negative charge is pointing toward it. Okay? So, if you have a mass, okay, usually a pretty big mass, but if you have a mass, no matter how big or how small, there are gravitational field lines associated with that mass. The trouble is they're very weak. Very, very weak. Unless you have an enormous mass like the sun or the earth or the moon, those are big enough to have significant field lines. Okay. But magnetic fields and poles are totally inseparable. But here's something that's also inseparable. Okay. If you had an electric charge, a singular electric charge, it could be either positive or negative. It has field lines going out around it, away from a positive charge toward a negative charge. You can have an isolated positive charge, or you can have an isolated negative charge. Okay, no problem. The field lines would be pointing toward that charge. You can have those, no sweat. You cannot have an isolated north magnetic pole or a south magnetic pole. You cannot. Okay? Poles, magnetic poles, always come in north-south pairs. The term for that is they're dipolar. That's not bipolar, that's a mental illness, but they're dipolar. They're always dipoles. I'm going to write it down for you if I can get the pen to show up somewhere. Does anyone see where the pen went? I can't find it anywhere. Look at that. I don't know why it did that. Let me go back to here. This is so aggravating. Okay, now I've got to move all this stuff around again. Okay, there's that done. This is what I want to get to. Okay, here we go. Now let's see if I can get my pen to write again. There we go. Okay. Magnets are always dipoles. Okay, dipoles. Field lines go from the North Pole to the South Pole. Here's another little thing, just like it is for electricity. Like charges repel each other, unlike charges attract each other. So similar, like magnetic poles repel each other, unlike magnetic poles attract each other. Okay? So same type of rule that you use for electricity as you use for magnetism. The difference is you can have an isolated positive charge or an isolated negative charge. You will never, ever, ever produce an isolated magnetic pole. Okay? Because on the other end of that, you'll have the opposite pole. Okay? And here was kind of an experiment that you could do if you wanted to, or try. I imagine someone has tried it before. If they had a magnetic material, magnet, say a bar magnet, broke it into two. Okay. Let me back up a little bit and show you something. Okay, here, this is showing exactly this. In fact, I'm going to advance it. Wow. Okay. It's not in here. It's in your book. I thought it used to be in the slideshow too. But let me show you a picture. Okay. Here is a picture of a very strong magnet. Now what is that at the ends? Those are called iron filings. Okay. Now I'll tell you what they've done. Now I'll tell you what they haven't done. They stuck this down into a group of iron filings, and all the iron filings associated with the poles. They did not associate with the middle. No one wiped them off there. Nobody. Now they did wipe it off the N here and the S there, just so you could see that's the poles, the North Pole and the South Pole. But no one wiped them off the middle part, because there is very little magnetic field in the middle of a magnet. It's not there. All the magnetic field lines are just like those iron filings. They stick out away from the North Pole and toward the South Pole. That's exactly how they were due. Now, if you had put a piece of paper on top of that magnet and sprinkled the iron filings on top, then you would have seen a pattern that I wish there was a picture in your book, but I don't know that there is one. Let me go back and just see. Oh, there, it was sort of like that. If you put a piece of paper over the magnet and sprinkled the iron filings there, they would pair up a lot like this. You see a big concentration at the north, a big concentration at the south, and you would see some of them line up around like this, and you would see those iron filings connect to each other and form almost these same field lines that you see here. It would just be an infinite number of them, okay? Not individual ones like this. And you can see that picture I just showed you is trying to do that. If you had had a piece of paper that would supported it, you would have seen that doing it, okay? Now, what if you took that magnet that I just showed you and broke it into two? Took the North Pole out here somewhere and said, hey, I've isolated the North Pole, over here isolated the South Pole. Hey, if you put that in more iron filings where you broke it, suddenly where nothing was sticking to it in the middle, now you got another a wad of iron filings on the two places where you broke it. So the place where nothing was, you broke it there, now you get more iron filings sticking there, because you cannot separate a North from a South Pole. Here's what they're meaning. If you took a big, long iron bar magnet, oh, here comes Valerie, glad she could make it today. So let me get her marked here. Okay. And just want to make sure I'm not running over. No, we've got plenty of time. If you were to take this long old bar magnet here and you dipped it in the iron filings, you have all the iron filings in the world here, all the iron filings you would want to here, nothing sticking in the middle. No. no trace of the magnetic field lines there. Break it into two, and suddenly, all of a sudden, you've got a south pole here and a north pole there. They weren't there before. As soon as you break them, there they are. Break them again, and now you got a south here and a north here, and a south here and a north there. You can keep breaking this as much as you want to until you get to an individual atomic setup there. You're going to have a south and a north pole lining up just like that. Okay? It's pretty remarkable. Where there wasn't any sticking of iron filings, now you have plenty of sticking of iron filings. Okay. Now, I don't know what this is over here. Shut that down, whatever it was. Oh, come on. What in the world is going on here? Okay. This is so outrageous. Let's go back to our PowerPoint show. I don't know what's going on here. Okay. Has it shut down my Screencast-O-Matic? I don't think so. Let me just see. Is that still doing? Yeah, recorder is still going, so we don't want to pause. Okay. I don't know what's going on here. It just went nuts. Okay. Let's return the meeting. It seems like that stopped. There, my bar is up in the middle again. I don't know what's going on here. It's enough to drive you nuts. And now it seems to have lost my PowerPoint. So let me go back and get my PowerPoint again. This is so aggravating. Okay. Okay. Go back to okay, we're almost there. Sorry, folks. This thing just seems to have a mind of its own. Okay, one of these days we'll get there. Okay, I think we've gone past that. Okay, I think we've gone past that. Okay, that's the one we were on. Okay, I'm going to try to get it back up again. Let's see if we can. Valerie, it's all your fault. Okay. I still don't see. Okay. This is so frustrating. I can see it right here. Okay. And then when I go to pull it up on Zoom, I'm sorry, here. Let's see. There it is. Showed up this time. Okay. We'll go back to the current slide. Sorry about this, folks. Okay. So we've already hit this slide all over the place. Magnetic field lines and poles are completely inseparable. You can't have fields without a pole somewhere. You can't have a pole without fields around it. Okay? Poles always come in north-south pairs. You can't separate them. In this illustration that you can't. If you tried to break them in two where there were no field lines before, suddenly you got field lines like crazy. You have no field lines here, break it in two again, you get field lines like crazy here and here, here and here. Everywhere you try to break it, you get more field lines. That's why those refrigerator magnets, you know, they're not very thick at all, and yet they're north-south poles. Now, for some reason, I seem to have lost all of you folks, okay? Can you see this PowerPoint? Yes or no?
No, we see our names.
Okay, I can't see your names. All I can see is the PowerPoint. So let me back off and see if I can find out what in the world this crazy thing is doing. Okay, let's go back to Zoom. Let's go back here. Okay, let's go back here and go back. Screen sharing has failed to start. Okay, I don't know why. Okay, here we go. I see your names again. So let's see if I can start it again. There it is. We'll go from current slide. Okay, there we are. But you can't see it, can you? Can you see my PowerPoint? I don't know why you can't. Here's the zoom. Okay, I'm going to close it again. This is so frustrating. Here's a screen share. There's what I want to share. Go from current slide. And now it doesn't show it. I don't know what's going on here. It's never, that I can ever recall, done this before. Okay, I'm going to close this, close that. No, I don't want to leave the meeting. Okay, I'm going to close this one. Okay, all right. Now, let's go back to screen share. And now, my PowerPoint is gone. Okay, so I'm going to close this again. Bring my PowerPoint back up again. This is so frustrating. Okay. Okay, here we go. Chapter 6, PowerPoint. Okay, welcome back. We were there a long time ago. Okay, I'm still trying to find it. Is that it? That's it. Why Zoom is, and here we go again. Okay. Go back to Zoom. Okay, let me go back to screen share, back to chapter 6, and back to from current slide. Okay. Now, can you see this? Every time I do this, it says screen sharing has stopped. Okay? You can't see anything. You just see your pictures again, right? Okay. There is what you see. Do you see my cursor go to screen share?
No.
You cannot see that. Okay. I don't know what Zoom is doing. Okay. I'm on screen share now. I double click on screen share. There's chapter 6. Can you see the PowerPoint there in a little box? No. Okay. Let me, all right. Let me try something else. I'm going to go to screen share here and go to the whiteboard. Screen sharing has failed to start. Okay. It won't do a screen share. Now, why it won't do a screen share, I don't know. Here's what I'm afraid I'm going to have to do. I'm going to have to Here it says screen share. Every time I do that, in the background, it says screen sharing has failed to start. Please try again later. Error code 105035. Okay. Now here's what I think I'm going to have to do. I think I'm going to have to shut down Zoom and bring it back up. I hate to do this. It's really a pain in the neck, but I think I'm going to have to do it. So I don't know if y'all are going to have to log back in or if you'll still be there. Try to hang there and let me see if I can do it. So I'm going to get out of this, out of that, and I'm going to get out of this, and it says I'm going to leave the meeting. Not end the meeting for all, but just leave it and see if I can come back. Okay? No, it won't let me do that either. Okay? So I think I'm going to have to end it, and then we'll bring it back up. Is that okay? See, hang there and see if I can get you back. So I'm going to end the meeting for all, and then, oh, here was a